In today's note, we are going to be exploring quadratic relations. So what we're going to look at first is just graphing quadratic relations from a table of value using an equation. So what we want to do for the following quadratic relations is we want to complete the table of values. We want to sketch the quadratic, so basically plot the points. We want to determine the first and second differences. And then we want to answer kind of the questions after each quadratic, and then the summary questions at the end. So this is kind of going to be an investigation. I'm going to lead you through the first couple examples. Then I recommend you pause the video to try it on your own. And then you can come back in and see how you did, and then kind of summarize with us. So here we're given an equation for our quadratic, y equals x squared. So we want to create or fill in our table of values for this. So what we have to do is, using these given x values, we want to plug that x value into the equation. So I know y equals x squared is my equation. So instead of x, I'm going to put -3, which is 9. Instead of x, it's going to be -2 for the next one, so -2 squared is 4. -1 squared equals 1. So all we're doing is we're taking the x value that's given in our table, plugging it in for x into our equation, and then solving for y. So 0 squared is 0, and we have 1, 4, and 9. And you do start to see some repetition here. That's going to be something you want to keep an eye on going forward. The first differences, if you don't remember from grade 9, the first differences, we can see in a definition down here. Basically, it's the difference in consecutive y values, or basically the rate of change of y values, or how are we changing from one value to the next in terms of the y values. So if I look at these two y values, how do I change going from 9 to 4? Well, you could do that math in your head, or if you know you're going from 9 to 4, you're decreasing by 5, so -5. Or you can do it mathematically, 4 minus 9, which equals -5. Right? Or bottom minus the top. Same thing for the next one. Bottom minus the top, 1 minus 4, -3, or we're decreasing by 3. And same thing, 0 minus 1, -1, or decreasing by 1. Same thing here, 1 minus 0, we're increasing by 1 now. Increasing by 3, increasing by 5. And that's our first differences. Our second differences is pretty much the same thing, except instead of looking at the change in y values, we're looking at the change in the rate, or in the change in the first differences. So we're going to do the exact same thing, -3 minus -5, or bottom minus the top, and this equals 2. How are we changing from -3 to -1? Well, we're increasing by 2. Or you could do -1 minus -3. 1 minus -1 equals 2. From 1 to 3, we're increasing by 2. From 3 to 5, we're also increasing by 2. So here we've completed our table of values. We found our y value. We found our first differences. We found our second differences. We've noticed, hopefully, that our second differences are all the same. And this is something that you're going to see with quadratics. With quadratics, the second differences are constant, or they're all the same. And this should be kind of familiar, because in grade 9 you would have learned that the first differences meant it was linear if they were all constant. So this is the same idea, except we're looking at the second differences, and we should see that the second differences are constant if it's quadratic. If neither of them are the same, then it's something else. If the first differences are the same, it's linear. So now that we've filled out the table, let's plot our quadratic, or plot our graph. So remember, A point is just an x and a y value. So if we look at the first one, negative 3, 9, that's our first point. So I go over to negative 3, up to 9. Remember, x comes first. When we plot it, x before y, you can think of the alphabet as well. X is before y. Negative 2 and 4. So go over to negative 2, up to 4. Negative 1 and 1. 0 and 0. 1 and 1. 2 and 1. 3 and 9. So there are points. If we plot our graph, again, as best as we can, there is our quadratic. And we should know, or we should see, that because we saw our numbers decreasing and then increasing, we saw that repetition of the same numbers when we found the y value, we can see that actually in our graph. We can see that they hit the same values as we go back up. So this graph does have some symmetry because it's the exact same on both sides. And that is our quadratic. So what we want to do now is answer these questions based on that previous graph that we just drew. So what's the direction of the opening? Or in other words, where is the opening of this graph? So if we roughly draw it or sketch it, that's roughly what it looked like. We can see that opening is at the top here. So that means that the direction of opening for this graph is opening up. The equation of the axis of symmetry, or the A of S, what the axis of symmetry is, it is basically an imaginary vertical line that divides our quadratic in half. Because it's a vertical line, we should know that it has the equation or the form x equals. In grade 9, you learned that the equation of a vertical line is x equals, and that happens to be whatever the x value is constant with that vertical line. So going back up, if I wanted to draw a vertical line that cut this graph in half, I would see that it would have to go right down through the middle here, right through this middle point. And so in this case, the x value that all these points along this vertical line would have would be 0. Doesn't matter where along this vertical line my points are, the x value is always 0. So in that case, the axis of symmetry is 0. The y-intercept, so where does it cross the y-axis? In this case, it crosses at 0, right? Because we had that one point right at 0, 0. Actually, let me go back up, we'll label it. So there's our y-intercept, 0, 0. The coordinates of the vertex. So the vertex is the turning point of the graph, where basically as we see our graph is going to decrease in one direction to a low point and then start to increase after it hits the vertex, or it might increase to a point and then start to decrease after it hits the vertex, or in other words, you could think of it as the highest or lowest point. So in this case, our vertex is going to be 0, 0. And if I go back up to my graph, I can see that if I start to trace my graph, we'll use a highlighter. If I start to trace, I'm going down, I hit my vertex or hit the lowest point, and now I start to increase back up. So that means that our vertex is also right here. So our vertex is also 0, 0. Our zeros are another word for x-intercepts. So basically, where does it cross the x-axis? And in this case, it crosses the x-axis at 0. Because again, if we scroll back up, we can see that the only time it touches the x-axis is right at this 0 value. It's a busy spot. It's the x-intercept of 0, 0 as well. All at that one point. And that's not always going to be the case, but in the most simple type, or most simple quadratic, it is. So our x-intercept is 0, the minimum or maximum value, or in other words, what we call the optimal value. In this case, it's the y value of our vertex. and we see our vertex over here, 0, 0. Again, remember y is the second value. So in this case, the y value of our vertex is y equals 0. So that is our max or min value, or our optimal value. And because it wants us to state if it's the maximum or minimum, if we look at our graph, because it opens up and the arrows are pointing up and the vertex is down here at the bottom, that optimal value is the minimum value, because it's the lowest that our quadratic is going to be. Because those arrows continue on up forever, that means it's going to continue going, or continue to get higher and higher, to increase higher and higher. So it's never going to have a highest or a maximum value. It's just going to keep on going forever. But it will have that minimum value of 0. So it is a minimum. Do you notice anything about the second differences? In this case, we did notice they are constant. They're constant or all the same, so we did notice that. And how would you describe the shape of this curve? And you can do it in one or two ways. You could describe it as a U shape, right? You could say it's symmetrical. But the term we're going to come to learn, basically any quadratic has a parabolic shape. Or basically it forms, or a quadratic forms a parabola, which is that U shape, or you might see it in an N shape in some other cases. So that's basically what we're going to be doing. I'll go through one more example, and then I recommend you pause the video to try to do some of these examples on your own. Again, you should have enough from these two examples to kind of get an idea of what we should be doing, but then I'll bring back the video with the full answers to let you look through. That way you're not listening to me talk for 40 minutes straight. So another table of values, we want to fill everything in. We have our equation number 2 over here. So the same idea for the y values. I'm going to plug in these x values. They're different, so make sure you're looking at the x values. So in this case, we'll have 0 squared minus 6 times 0 plus 5. So all I did was I plugged x equals 0 into this equation, and I'm going to solve for y. And when I do, I get 5. Then 1 squared minus 6 times 1 plus 5, and I get equals to 0. Same thing with the next one. I'm going to plug in a value, plug in the x value, and solve for y. So 2 squared minus 6 times 2 plus 5, and I get negative 3. And if I continue this for every x value, I should get negative 4, negative 3, 0, and 5. So again, we do start to see that repetition, which tends to, or leads us to believe that we do have kind of the right points going on. Our first differences, remember, how do the y values change? So from 5 to 0, or from 0 minus 5, we get negative 5. 0 to 3, or negative 3 minus 0 equals negative 3, or decreasing by 3. Negative 4 minus negative 3 is negative 1. We're decreasing by 1. And as we continue, 1, 3, 5. So those are our first differences. We notice that our first differences aren't the same, so it can't be a linear equation. If we look at our second differences, so again, the same idea that we just did, except we're looking at our values of the first differences. So negative 3 minus negative 5, we get 2. Negative 1 minus negative 3, we get 2. And so on. If we continue doing the bottom minus the top, we should see that our second differences are all 2, which leads us to believe that this is going to be a quadratic graph. which is good because that is what we're graphing. We go to plot our points now. So remember, x and y is a point, so that is what we're going to be plotting. So 0 and 5 is our first point. 1 and 0 is our next. 2 and -3. 3 and -4. 4 and -3. 5 and 0. 6 and 5. And we start to see again that repetition or that symmetry that our quadratic or that all quadratics have. So there's the graph of our quadratic. Y equals x squared minus 6x plus 5. Now with the same questions we're going to have to do, I'll start drawing it on this page, that way when we go through the next, it's a little bit easier. We're going to need to find our axis of symmetry, which is that imaginary vertical line that cuts it in half. And in this case, the vertical line always goes through our vertex. It's going to have the form x equals, because that's the equation of a vertical line. What x value does it always go through? Well, if we follow it down to the x-axis, we see it crosses through 3. So the equation of our axis of symmetry will be x equals 3. If we want to find our vertex is down here. And we can see that point is at 3, -4. Our x-intercepts, if we want them, we can see that they cross the x-axis here. So in this case, I have 2 of them now. So at 5 and 0. And here, x-intercept of 1 and 0. And I can see that I have a y-intercept up over here where it crosses the y-axis of, in this case, 0 and 5. So there we have all of our key points. So now we can go back and answer the questions. And if you have to pause and rewind to go back and look at this, or hopefully you've copied this graph down on your own, then it should make it a little bit easier. The direction of the opening. So again, we saw that the opening of our quadratic was at the top. As well, what you could have seen, where are the arrows pointing at the end of your graph? In this case, they're pointing up, so our direction of the opening is up. The equation for the axis of symmetry, we saw that that was x equals 3, because that was the vertical line that divided our quadratic in half. The y-intercept, in our case, was 5. The coordinates of the vertex were 3, -4. The zeros, in this case, we had 2 of them. We had 1 and 5. Those were the 2 x-intercepts. And our maximum or minimum, or our optimal value, we had it was y equals -4, or the y value of our vertex. And in this case, it was a minimum. Because again, the direction of opening was up, so we're always going to have a low value, or a minimum value. What do we notice about the second differences? They're constant, or basically all the same. How would you describe the shape of the curve? Right, so again, you can go through all the other ones, the U shape, the symmetrical, parabolic, or basically it forms a parabola. So what I want you to do now is pause the video. You have 2 more or a couple more examples to try to go through, doing the same idea of creating a table of values, finding the first and second differences, and then answering the questions, or basically finding kind of these key points of our parabola. So I'm going to pause the video in a second, take some time, and then we'll come back and then give you a chance to kind of check your work. So what you should see now, if you've tried it on your own, hopefully you're joining back with us. But this is basically the next one filled in, going through the exact same steps we did, just a different equation. Right, so we found our y values by plugging the x values into the equation and solving for y. Found our first differences by seeing what is the change in y, or what's the rate of change of y. And then the second differences, we're basically finding the rate of change of our first differences. Again, we should see that our second differences are all the same, and if we want to label kind of the points before we move on to the questions, this is roughly what it should look like. Now, in some cases, like our x-intercepts, we may have to approximate because they're not going to nicely cross a value or a grid line. So we're just going to have to approximate it, which is fine for right now. And our y-intercept, we may have to continue on our table of values to find out what that value actually is. Which in this case it would be -10. So looking at the questions, again, you can get most of them from looking at that graph. This is an example where the direction of the opening is down. So this is a little different from what we've seen before, because now we can see that it's opening down. So hopefully you can see the difference between something that's opening down and something that's opening up. The equation for the axis of symmetry, x equals 4, y-intercept was -10. The zeros or the x-intercepts we had to approximate. And again, the vertex is that lowest or highest point, that turning point of the graph. The y value of your vertex is your maximum or minimum. In this case, it's a maximum because we're opening down. And again, the first differences are constant and the shape is still parabolic. If we look at the fourth example, again, hopefully you tried it on your own. Again, same idea, exactly what we did before. Plug the x values into the equation to solve for y. You have your first differences, your second differences, and I've labeled kind of the key points on our graph. Again, the x-intercepts in this one we had to approximate a little bit, but other than that, everything else we should be able to get from looking at the graph or our table of values. Again, for stating these, this should have been very similar to the last one. Like I said, the zeros you'd have to approximate roughly, but other than that, everything should be fairly straightforward, based and very similar to the other examples that we did. And finally, the fifth equation, again, same idea again, plugging the values into the equation to solve for x. This one may be a little bit trickier because we're dealing with some larger numbers, but as long as you're using a calculator, the steps are still going to be the same. First differences and second differences are the same regardless of the numbers. Again, we see that even though we have bigger numbers, our second differences are still the same. In this case, our x-intercept and our vertex tend to land on the same spot. We don't have a y-intercept in this one, or at least from what we can see on the graph. So you could plug in when x equals 0 and solve to find the y value. That is one option as well. So when we plug everything in, or when we answer the questions, this one opens up. The axis of symmetry should be easy to tell, that vertical line. The y-intercept, if you didn't plug x when x equals 0 into the equation to solve, it is 48. Coordinates of the vertex, -4, 0. We only have 1 0 this time, or one x-intercept, which is -4. We do have a minimum value now because it's opening up, and again, it's constant and parabolic. So again, this was more of an investigation just to get you comfortable with entering numbers into an equation to come up with a table of values and then graph that accordingly. And it does give us a brief introduction to some of the key points or key properties of a parabola or a quadratic relation, and what to look for, or what we might be encountering.